Mixing problem is very common in many scientific and engineering fields. They occur whenever we have situations involving the mixing of two or more substances within a container. For instance, in chemical engineering, refinery processes are optimized by modeling mixing phenomena in reactors, pipeline, and storage tanks. In environmental science, the dispersion of pollutants is predicted by modeling the spread of pollutant in a lake or river. In food science, efficient techniques are developed for mixing by designing brewing and fermentation systems. In atmospheric science, researchers analyze climate change by simulating the mixing and interaction of different greenhouse gases in the atmosphere. Next, we move on to the background information for turning a circuit. Turning a circuit is a process of adjusting its components to achieve a desired response at a specific frequency. This concept is particularly important in RLC circuit. Take a radio for instance. It is designed to receive a specific radio station that transmits at a particular frequency. Without a turned circuit, the radio would receive a chaotic mix of signals from various stations, making it impossible to listen clearly. Tuning enables the circuit to selectively respond to the desired frequency while effectively filtering out unwanted ones. There are two common ways to turn a circuit. For instance, one way involves adjusting capacitance, while the other way is to adjust inductance. These techniques are commonly used in alerting the resonant frequency of the circuit to resist specific stations. Next, I will describe the methodology for the mixing problem. To calculate the amount of salt left in the tank after T minutes, we first define the variables. Secondly, we set up the differential equation governing the amount of salt in the tank. It found that it is a first-order linear differential equation and can be solved using the integrating factor method. Lastly, we take t equal to 60 as an example to substitute it into the equation of 10 to calculate the amount of salt left in the tank after 60 minutes. Next, I will describe the methodology for turning a circuit. Firstly, we substitute the given information into the differential equation for the RLC series circuit. It found that it is a second-order linear differential equation and solve it to obtain the general solution for the homogeneous linear equation. Secondly, the method of undetermined coefficient is utilized to find the general solution for a non-homogeneous differential equation. After that, we substitute the initial condition given to obtain its particular solution. Lastly, the particular solution is applied to investigate the changes in the charge on the capacitor over time.
My name is Chong Wei Yee and my match number is 292804, and I will continue with the problem 1, which is missing problem. Missing problem is common across many scientific and engineering fields that occur whenever we have situation involving the missing of two or more substances within a container. In this situation, a tank contains 1,000 of liters of water with 50 kilograms of dissolved salt. A mixture of 2 grams per liter flow into the tank at a rate of 10 liters per minute. In this, we will assume that the solution is mixed thoroughly and drained from the tank at the same rate as it flow in. Hence, in this situation, the finding will be about how much salt will be left in the tank after T minutes. The information given is shown below, which is the mixture flow-in rate will be equal to the mixture flow-out rate at 10 liters per minute, and the initial salt in the tank, which is Q0, will be equal to 15,000 grams, and the initial amount of water in the tank will be 1,000 of liter, and the concentration of mixture is equal to 2 grams per liter. And we will continue with the calculation of the rate in and rate out. So in this case, we will be letting the R1 be the rate in of mixture into the tank, R2 be the rate out of mixture from the tank, and the QT will be the amount of salt will be left in the tank after T minutes. And we will get that the R1 is equal to 20 grams per minute, and the R2 will be equal to QT over 1,000 grams per minute. Next, we will continue with determine the rate of change of QT. And here we will show that there is a first order linear differential equation, and from this we realize that we can apply the integrating factor method. By using an integrating factor, the first step we should substitute the e power of 10 over 100 into the equation 1, and we will find the Qt is equal to 2000 plus constant e power of negative t over 100. Next, we will continue by substituting the Q naught equal to 15,000 gram into the equation 2, and we will find that the C constant is equal to 13,000. Hence, we can conclude that the equation of the amount of salt will be left in the tank after 10 minutes will be Qt equal to 2000 plus 13,000 e power of negative t over 100. Next, we will continue by letting t equal to 60 minutes to find the amount of salt that will be left in the tank. We will substitute the 60 into the t, which is we will get Q60 equal to 2000 plus 30,000 e power of negative 60 over 100, and we found that the answer is equal to 9,134.5513 grams. In this case, we can conclude that after 60 minutes, the amount of salt left in the tank is equal to 9,134.5513 grams.
Hi, my name is Chum Yao Hui and my matrix number is 292327. Now we are going to talk about the problem 2, which is starting a circuit. In this scenario problem, the Adam is carrying the final physics lab test to investigate the charge applied to the capacitor in the RCL series circuit. He is recorded the parameters shown as below, which is L is equal to 10 over 6H, R equal to 20 ohm, C is equal to 2 over 15F, and the ET is equal to 600 volt. And in this scenario, we assume that the initial charge on the capacitor is 0 coulomb and the initial current is 8 ampere. The governing differential equation for electric potential is shown by above, and it can be found by substituting the VR, VL, and VC into the Kirchhoff voltage law, where VR, VL, and VC are the voltage across resistor, inductor, and the capacitor. First, we can substitute all the coefficients that we find inside the differential equations and followed by divided it by 10 over 6, and we can rearrange and setting the equations by let q prime equal to dq over dt and q prime prime equal to d square q over dt square. And at last, we can find equations of q prime prime plus 12 q prime plus 4.5 q equal to 360. And we found that this equations is known as the second order linear differential equations with degree of 1. Now we are going to find the general solution for the reactive potential. The first step is to solve the second order homogeneous linear equations by finding out its complementary solutions. First, we can assume Q equal to e power of Rx, Q prime equal to Re power of Rx, and Q prime prime equal to R square ERX. After that, we can substitute this into the differential equations, and followed by using the method of converting the square, we can find out that two real and difference roots, and the first root is negative 0.3875 and the second root is negative 11.6125. And finally, we get our homogeneous linear equations, which is C1 e power of negative 0.3875t plus C2 e power of negative 11.6125t. Next is to find the particular solutions by solving the non-homogeneous equations. We are assuming QPT equal to A, and we differentiate it 2 times to get Q prime PT and Q prime PT. After that, we substitute back it into the differential equations and we find that the A is equal to 80. So we can assume that our particular integrations QPT is equal to 80, and we can get the general solutions of the electric potential is equal to C1 e power of negative 0.3875 t plus C2 e power of negative 11.6125 t plus 8t. Next, we need to find the coefficient of C1 and C2. At first, assume that the initial charge Q0 is equal to 0, and then we sub into the differential equation and we find that the C1 is equal to negative C2 minus 8t. And the initial current is equal to 8, and current is also the rate of change of charge. So we need to differentiate one time of our differential equations, and we sub 8 into the differential equation, and we found that the 8 is equal to negative 0.3875 C1 minus 11.612562. By solving the simultaneous equations, we have finally find the C1 is equal to negative 82.0490 and the C2 is equal to 2.0490. And finally, we get our general solutions, which is equal to negative 82.0490 e power of negative 0.3875 t plus 2.0490 e power of negative 11.6125 t plus 80. And the last step is to find the change in the charge of the capacitor over the time. And in this scenario problem, we test the change in charge of capacitor for 1, 2, 3, 4, 10, 100, and 1000 seconds. And we can finally find that the maximum charge of the capacitor is equal to 80 coulomb over the time.
In conclusion, we analyzed the flow rate of salt into and out of a tank containing a salt water mixture. Starting with 15,000 grams of salt in 1,000 liters of water, we derived the differential equation governing the salt amount over time. Solving this equation revealed that the amount of salt in the tank after 60 minutes is approximately equal to 9,134 and 55 grams, showing the dynamic change in concentration towards stabilizations. For the RLC circuit problem, we examine the charge on a capacitor over time in a series circuit with given inductance, resistance, and capacitance. Using Kirchhoff Kirchhoff voltage law, we derive a second-order linear differential equation. The nature of the root of the characteristic equation determines the behavior of the charge over time. Solving this with the initial condition, we found the maximum charge on the capacitor to be 80. This example demonstrates the importance of ordinary differential equation in various domains that help us understand mechanical system, electrical circuit, wave propagation control system, population dynamics, and economic change. Through this equation, we gain valuable insight and solution to complex real-world problems.